Hello friends, today we'll discuss what is more important to know while two pump is operating in parallel. So we'll discuss today based on the pump curves. Let's say we have two pump, one is this and one is this, and both pump are operating in parallel, so delivering. So this parallel operation means the flow is, let's say this is tank, our tank, the flow is coming like this and going, delivering somewhere. Okay, so 1 2. So as we discuss, each pump has pump curve like this is head versus flow curve. So let's say we have one pump curve, it's like this. Now let me draw a little bit further. So this is our one pump curve. Now I would like to draw pump curve while two pump is operating in parallel. So let the same curve we draw it here. So it's like this. So this is head versus flow curve. So this is one pump curve. Okay, any one or two. Now the parallel operation pump curve, I told you how we draw actually. See, if you do want to draw the pump curve, means the parallel pump curve, so how you will draw? So take some point here, Q1, Q2, Q3, Q4, Q5, from start of pump curve to the end of pump curve up to this point. Take some flow and correspondingly note down the head. Say some this here, note down the head, means based on this point maybe some head H1, based on this point maybe some head H2, like this, and according to this point, this point, this point, and make a table. Let's say this is Q, this is H, so this is Q1, Q2, Q3, Q4, correspondingly get the value of head from this curve. Now you want to draw a pump curve for parallel operation. So what you need to do, the flow will be this flow will increase, head will be constant. So the new flow, now you don't have for a new this parallel pump curve, what you need to do, head you will keep the same, but what you will do, this Q will become Q1 plus Q2, Q1 plus Q2, so Q1 plus Q2. So accordingly you can draw the pump curve. Now use these two values to draw this pump curve. So it will be like this. So what is, you see what is more important here actually, operation wise. See, while pump, let's say initially our resistance is here, we have, let's say we have a control valve here, flow control valve here, you say it's FCV. So initially let's say we have opening around 50%, so the resistance there. Now we increase our opening to 100%, so the resistance will be less now because it will be like this here now. So initially while two pump is operating, so our operating point was here, so OP1 I would say. Now sorry, it will in parallel operation, now it will be here, so OP2, this is my operating point 2 now, because I increase the opening of the flow control valve, so the resistance is decreased across this control valve. So that means this resistance curve will move in a right direction like this one to reduce the This is resistance curve of a pump. Okay, so what is happening actually, if let's say our operating point, initial operating point is somewhere here or here, and we open the control valve to 100%. Let's say initially it is 10% open, so our operating point of the parallel operation may be somewhere here, and when we open it 100%, our operating point shift to right, of course, like here. So at that moment of time, while in operating in parallel, see here corresponding flow is here and the corresponding flow is here, and the head is also is almost same. So the parallel operation also will not give you the much advantage of increased flow rate. But if you see the end of curve operation, toward the end of curve operation on the right of the pump curve, here the gap in these two curves, parallel operation curves, is single operation and the two parallel operation curve is higher. So that means when you are operating right side of the pump curve from the BEP, somewhere let's say BEP is here, so right side of the BEP, at that moment of time, it depends on how much throttling you are using for your FCV to operate, because you need higher opening of your FCV to operate the pump toward the right side of a pump. So at that time you will have a higher gain in flow rate, but slightly higher loss in head also. But the head will, you don't have to worry when you are in parallel operation, that you are most you are more worried about the flow, not a head, because head you are achieving with the single pump also. So your requirement is to increase the flow rate with the same head. So head will not be lower than your previous your single pump operation, but your flow, you will get substantially increased flow rate while you are operating your pump on the right of a right side of the pump curve. But when you are operating the pump toward the right side of a curve or BP, at that time what will happen, if you see the power curve of a pump, it is like this, it is like this. So at that time, toward the end of this is power curve, actually power curve, power consumption curve of a pump. So when you are operating toward right, so after BP the curve is exponentially, means slightly increasing in a higher rate. So that means when you are operating pump on a right side of the pump curve, so your power consumption also increase and your NPSH also increase, because NPSH curve is also similar to this curve, like this, like this. This is NPSHR, that also increase, but the gain is higher here. If you see, because in lower side, left side, the flow gain is not very high actually, but we know that it will be double. But it also depend on your FCB. If it's 100%, of course it will be double, but when the opening you reduce, so it will not be double. So according to the operating point, the flow and head will be there in the parallel operation. So this is what I want to tell you about some more thing in pump parallel operation, what you need to keep in mind when you are operating your pump in parallel. So in the next video I will tell you about the FCV, how we size the FCV actually, what is the basis of FCV sizing. Let me explain you here, we should not wait for a next video. So I will tell you, let me erase something here to draw. So I would like to tell you what is the work of a process design engineer for FCV sizing actually. Say FCG is a kind of control valve, right? control valve. We can draw it like this also. We can draw in many way actually. We can draw like this also, and we can put a cap like this. So this is more better. So this is my control valve. So you know the characteristic of a control valve is defined by its CV value. Okay, so how we calculate the CV value? See, based on our process requirement, we know what will be our normal flow, normal pump flow, what will be our minimum flow, what will be our maximum flow. Okay, so these three things we know. We also know the fourth thing, fluid properties, because process engineer do simulation, he know everything about the fluid. So fluid properties he know, mainly physical properties or thermodynamics properties of a fluid, because we least bother about the chemical properties in these phenomena, in physical phenomena in machine. So we bother more about the physical property like density, viscosity, specific gravity, heat capacity. These are the things. We more worried about the process fluid velocity, the vapor pressure. So we know about this, and we also know the size of piping means what is the size of inlet outlet piping of a pump, and what is the size of a control valve, means the piping where the control valve is installed, means FCV is installed. So now we know three flow. So based on this three flow, we also give value that allowable pressure drop. See, somewhere we are sending our fluid, so we know what would be the pressure there, what is the requirement of pressure there. So when the pump is operating at minimum flow, so see here, I will tell you here. So minimum flow, I will draw three pump curve, three resistance curve. So flow is minimum, that means here corresponding to this is 1, 2, 3. So this is 1 minimum, this is normal, this is maximum. So here you draw it, here you draw it, here you draw it, here. So this is Q minimum, this is Q maximum, sorry, normal, this is Q maximum. Okay, so at this point of time you can see this is at this flow it is delivering head H1. At this point while operating it's delivering S2, and at this point it is delivering head S3. So but our head requirement at the discharge where we are sending it, right here, it is fixed. So that means at minimum flow it is delivering high head, but our head requirement is same, and at minimum flow the pressure drop in the system will also be less. So at that time available delta P is higher, we have higher delta P available. At normal flow it will be medium available, and at maximum flow, when it is, see, at maximum flow the head it is delivering is this much, but our head requirement is H. So that means at that time, so available delta P while doing the hydraulic calculation for FCV, so we need to check the available delta P for FCV at different flow rate. So it will be minimum. So at higher flow rate, so the available delta P will be minimum for FCV. This is what I am discussing, the work of a process design engineer. I am not discussing the work of instrumentation because they comes later. This is first our baby, FCV. Later on they do the specification based on the standard or standard guidelines to purchase, give the purchase order to the vendor. Actually that's what they do, because the basic sizing calculation and basic input provided by the process design engineer for any FCV sizing, right, or control valve sizing. So that's what I'm discussing. When I'm discussing what a process design engineer do, you can understand that what is our input and how precious these values are for instrumentation design engineer and further buying and procuring this control valve. So based on our operation, pump operation or process requirement, we know what is our fixed head requirement here and what is available pressure drop what could be here for FCV while operating at different flow rates. So because we know how the pump is operating, from the pump curve we only came to know how the pressure drop will be available for different flow rates. So we have defined the pressure drop values for minimum, normal and maximum flow here. Okay, now it is the now let's say I will just erase to have some space here. So actually now the main thing is we know the pressure drop, we know the values of flow rates for FCV sizing. So we have minimum flow, normal flow, maximum flow. So as I told you, let's say we take example for minimum flow Q, QM, QN, QM. Here we have, let's say available pressure drop is at minimum flow available pressure drop for this FCV is 1 bar. Normal it is let's say 2 bar. This is 1 bar. This is 0.5 bar. And we know specific gravity of fluid. So let's say it's water. So it's 1. Now we know this formula for pump this liquid control valve sizing. So it is Q equal to CV under root of delta P over specific gravity. Okay. Now this is the simplest formula, but there are factors to be included actually in this. Q equal to CV. Here we have flow recovery factor, orifice discharge factor. So these are two major factors. So we can, it's like this. So delta P over specific gravity. If our recovery factor in this one it is recovery factor is 0.8, I think 0.8, and this is 0.3 or 0.4. You can take like this. It can be 0.6 to 0.8, 0.3 to 0.4. So flow you need to put in GPM, and then put this value 0.6 to 0.8, any value between this 0.3 to 0.4, and delta P you have also calculated delta P here. Okay, this is a specific gravity, you know, so based on that you can calculate the CV value, and this CV value calculated is based on 100% opening. So whatever CV value you are getting, let's say you got 10 CV value, so now this is at 100% opening you have calculated. Now normally for sizing FCV or any control valve we keep the opening of 50%. So whatever you got CV values, so the actual CV value for 50% opening will be divided by 0.5. So it will be like this. So around 20. So whatever you got, just double it. So this is all about the FCV sizing. Thank you for watching my video. Bye bye.